Thank you very much. Good morning, everyone. Yep, my name's Tamsin. I'm a climate scientist. I work in the Department of Geography at King's College London, although, as I was just telling Tom, I actually studied physics at university. There's lots of different ways you can go into climate change, and I'm going to mention that right at the end of the talk as well. I've got a quiz question for you. What is the average temperature of the world? So in a minute, I'll get you to put your hands up. I'll go through the answers first, the possible answers first. Is it A, 0 degrees? Is it B, 15 degrees? C, 5 degrees? Or D, 25? So let's say hands up for A. We've got a few tentative A's. B, 15 degrees? Quite a lot of you. Yeah, maybe half, I think. C, 5 degrees? Quite a lot of you there, and D, 25 degrees. Yeah, so kind of maybe split fairly evenly between B, C, and D. The answer is 15 degrees. And we're very lucky that it's 15 degrees because, of course, we need liquid water on this planet. We wouldn't want it to be too cold, and actually the greenhouse gases that are warming our atmosphere at the moment, we need some of them to keep our planet at this 15 degrees. We just don't want too much of it. That's what I'm going to talk about, obviously, for climate change. Second question, how much have global temperatures increased by just in the last 50 years or so? Okay, so we've got four answers: 0.1 degrees, we've got 0.5 degrees, we've got 1 degree, and we've got 5. So have a think, 50 years. Okay, hands up for A. 0.1. Couple of people. B, 0.5. Yeah, a few more here. C, 1 degree. Loads of you saying 1 degree. And D, 5 degrees. A few of you there. Well, it's actually half a degree, so well done, you guys. But I can see why some of you might have said 1 degree, I can guess, because that's a number you might have heard of for a bit longer ago, which is since the pre-industrial period. So since the late 1800s, it's a bit after the beginning of the pre-industrial, we've had just over 1 degree of warming. So that's maybe what you were thinking of there. And this is a map from the latest report from the Intergovernmental Panel on Climate Change, the IPCC. Hands up if you've heard of that IPCC, Intergovernmental Panel. Yeah, well done, a few of you. So that's a big report that summarizes all climate science every few years to give to governments to make their decisions on climate change. And I was one of the, I think, over 200 authors of the one that just came out in August. It was in the news, putting together all of climate science. And this shows that the global warming of 1 degree on average over the whole planet is not completely evenly distributed. So we've got more warming actually over the land than the oceans, and we've got more warming in the Arctic up in the North Pole there. We've actually got a cold spot there, and all of this warming, so it's affecting every part of the planet, is basically down to us. And even that cold spot, funnily enough, we think is down to us because the ocean currents that normally bring heat up from the equator towards kind of the North Atlantic and Greenland have been slowing down a bit, so it's been a bit cooler up there than usual. So 1 degree of warming. Why does 1 degree matter? It doesn't sound like very much, does it? You know, obviously the temperature just from hour to hour can change that much, but it's all about the average temperature of the planet and what it does to our weather and to the oceans and the ice sheets, as I'm going to talk about. There was a really dramatic thing that happened this year based on extreme heat, which I'm going to show you a video of. Back in June this year, there was a record-breaking temperature in Canada, Western Canada, of sort of nearly 50 degrees C. And there were lots and lots of wildfires all along the west coast of North America, of Canada and the USA. And this was a town called Lytton, also known as Kamchin in the original, for the original indigenous people, the native people. And they had wildfires, of course, made a bit more likely by the fact that there was that extreme heat. And the village, unfortunately, mostly burnt down, so very serious sort of representation of climate change there, and 2 people died as well. And so the point about this 1 degree of warming is that it's already changing our weather. It's not something that's going to happen in the future, it's already happening. So we've got changes in things like extreme heat, like I just showed, and we've got changes in heavy rain, and we've got changes in drought. So that's when you get less rain, but also dry soil. because of the heat. And so just to give you an example, if you had an extreme weather event that you'd normally expect once in every 10 years before humans started putting greenhouse gases into the atmosphere, then that is now happening about 3 times more likely for extreme heat, about 30% more likely for heavy rain, and it's 70% more likely for drought. So that's just to say, really, that climate change is already affecting our weather a bit, and of course it's going to affect things more in the future, the more warming that we see. And some of these changes are really unprecedented in thousands of years. So this white area here over the ocean is the Arctic sea ice. So that's the floating ice over the ocean in that, remember, that warmer Arctic area up in the North Pole. That sea ice has been decreasing since we started measuring it with satellites in 1979. And this yellow line shows the kind of average period you can see there as well. So last year, that sort of white area there was the second smallest since the satellites sort of started measuring it. The sea ice actually expands and contracts every year with the season, so it's biggest in the winter, of course, and smallest in the summer. So the September month is when we get the minimum sea ice that sort of gets the smallest. But it's basically sort of over the last 10 years or so, that sea ice has been smaller than we've ever seen it actually in about the last 1,000 years. And some of the changes go back even further than that in terms of how unusual they are. You might have seen a warming stripes picture like this before. This shows the temperature of the planet. Every stripe is a year in the past, and it goes from at the left-hand side 2,000 years ago through to the right-hand side today. So each stripe is 1 year. And you can see, obviously, in the recent years, since about 1970 or so, there's much more warming, and that warming is also unprecedented in 2,000 years. This is a little glacier in Iceland. This is called Ok, Ok. And that glacier was the smallest in Iceland, and unfortunately, a few years ago, it disappeared. The smallest glaciers are the most vulnerable. And actually some artists put up a plaque sort of saying, goodbye and kind of marking its loss. You can see the words here. This monument is to acknowledge that we know what is happening and what needs to be done. So they were, really wanting to mark the occasion for future generations. And these glaciers have been retreating around the world. Most glaciers around the world are retreating, and that since sort of the 1950s or so has been, again, unprecedented in about 2,000 years or more. And sea level rise, the area that I work on particularly, since 1900, that's been faster as well since the last 3,000 years or so. And that sea level rise, of course, makes flooding at the coasts more likely. So when you get things like a big hurricane, this is Hurricane Katrina, quite a few years back now, but a very serious hurricane. When you get a big hurricane like that and it causes a big surge in water with the storm, then that's going to be worse when you've already got sea level rise on top of it, so that flooding is going to be more likely. Okay, another question. When was the last time there was this much carbon dioxide in the atmosphere? So we're at about, 415 or so parts per million. So we've got kind of carbon dioxide has been increasing in the atmosphere because of our emissions from things like industry. So when do you think the last time was that there was this much CO2 in the atmosphere? So the answers are 350 years ago, 130,000 years ago, 3 million years ago, or 350 million years ago. Right, have a think. Okay. It's good, you can talk to your neighbour for a sec. Okay, hands up if you think it is A, 350 years ago. Can't see any, I don't think. B, 130,000 years ago. Yeah, we've got a few, so that's the kind of last time we've had sort of ice age cycles. That was a period when it was kind of warm before the most recent ice age. 3 million years ago. Yeah, a few of you, yeah. And D, 350 million. All right, so you went for the most dramatic. It was 3 million, so well done to you. So around 3 million years ago is a time called the Pliocene. And when the CO2 was that high for a long period of time, it got warmer. The Greenland ice sheet didn't exist. It was about 3 degrees warmer than the sort of pre-industrial period, and basically no sort of modern humans. Okay. So what's going to happen in the future? That's my job as a climate scientist, to try and figure that out and to tell it to you and to tell it to governments to try and make decisions about the future. Now, I work with computer models to predict climate change, and it took me a really long time to even think about the fact that climate models existed and computer models existed, and now I use them in my job. Computer models basically are made of the whole planet using just any kind of computer code, lots of different kinds, to simulate the planet. So just like you get kind of games that simulate reality, that you can kind of play around with reality. In a way, it's just the same thing. You can play around with the carbon dioxide in the atmosphere and see what it does to the temperature. So here we've got temperature in our computer model, and you can see it's quite sort of pixelated, like a very low number of pixels camera. It's kind of blocky looking. And we use these computer models to try out different scenarios of the future to predict what's going to happen. And we can kind of think of choosing from one of a few different possible futures. And I say choosing because obviously we've got a choice about what we do with our emissions. We'll be talking about that a lot today, I'm sure. And these are 3 kind of possible worlds of the future I want to focus on. So on the left-hand side, we've got a world that is 1.5 degrees of warming. So remember, we're at 1.1 now, so just a little bit more warming, a little bit more change. And we've got temperature change at the top, and we've got rainfall changes at the bottom. And the reason I picked 1.5 is because it has something to do with this thing, the Paris Agreement. So hands up if you've heard of the Paris Agreement. Yeah, some of you. So the Paris Agreement was a big global decision back in 2015 to really try hard to limit global warming to 1.5 degrees. The sort of official phrasing was to pursue efforts to limit warming in the future to 1.5 degrees. And the second one in the middle kind of scenario is a 2-degree scenario. And that was also mentioned in the Paris Agreement because we said we agreed that we would keep global warming well below 2 degrees. We really want to keep it below that 2-degree limit. Okay, so those are the kind of the lower and the upper bounds of this Paris Agreement, where all of the governments, all of the countries of the world got together and said, we agree to do this. We're not quite sure how yet, but we agree to have this goal. Now, this 4-degree world at the right-hand side, that's the kind of, what would happen if we just kept on increasing our emissions of greenhouse gases every year, maybe sort of doubling them by the end of the century or a bit more. And so by the end of the century, we would get to something like 4 degrees. Now, again, 4 degrees maybe doesn't sound that much, but you can see some of the temperature changes here are really big. But also that Pliocene period, remember, 3 million years ago, was only 3 degrees warmer than pre-industrial. And that was actually the last time that temperatures were sort of above 2.5 or so degrees for any kind of length of time. So a 4-degree world would be really different from anything we've seen for about 3 million years. So not something we want to head for, but I don't think we're going to, and I'm going to say why at the end. So the rainfall, so the temperature patterns you can see here are a bit like I've already said. So we're going to see in each of these worlds more warming over the land and in the Arctic. You can see the South Pole starts to warm up more as well. And these rainfall patterns, basically the blue and the brown are showing more rain and less rain. And it's a complicated pattern, but the sort of general picture is actually an amplification of the Earth's water cycle. And what that means is that everywhere that tends to get a lot of rain already will get wetter, and everywhere that tends to be dry at the moment will get drier. So it kind of amplifies that sort of water cycle to make it wetter in the wet places and drier in the dry places. And so all of that sort of together means that the more warming we see, whether we have 1.5 degrees, 2, 2.5 or 3, we get more of those changes in extreme weather that I talked about. So for example, in the extreme heat, something where we normally would expect it 1 in every 10 years before our influence. starts to become 4 times more likely, 6 times or 9 times more likely in these different worlds of 1.5, 2 or 4 degrees. And you can see that the same thing happens for heavy rain or drought. Each half a degree of warming, each degree of warming basically makes those things more likely. And I think it's important to sort of remember that with climate change, some parts of it will be reversible and some parts of it won't. So the extreme weather that I talked about, if we manage to one day get our temperatures back to those pre-industrial levels, to the kind of original temperatures back from the 1800s or so, then we think those changes in extreme weather will just reverse back to normal, because as the temperature of the planet cools down again, things like heat waves will reduce again. And things like that Arctic sea ice loss that I mentioned, if we warm up the planet and lose Arctic sea ice, we think that if we cool the planet back down again eventually, which we think we can do eventually, then that Arctic sea ice would grow again. So that's kind of important to hold on to, is not everything we're doing is irreversible. But the kinds of areas that I work on are more the irreversible changes. So things like the ocean warming, it's very slow to warm up, it takes a long time. There's a kind of a long response time, if you like. It's very slow to keep going. And the ice sheet changes, the Greenland and the Antarctic ice sheets that I'm going to talk about. I'm going to talk about Antarctica in more detail. And therefore the sea level rise. Those are things that probably will be around for hundreds, possibly thousands of years. So the sea level rise is because of the ice sheets melting, the glaciers melting, but also that ocean warming as well, because we've got the waters expanding as they warm. Okay, so now we're going to take a little bit of a tangent into Antarctica. Now, excuse me. Sorry, I just got a dry throat. So I work on Antarctica, and it is a really, really interesting place to study as a scientist, because we don't know that much about it. It's obviously really inaccessible. It's hard to get there. It's hard to go and take measurements. And it's a very kind of complex beast, if you like. It's a very complex environment, as you might remember when you studied it. So I'm going to show you some cutting-edge science now of the last few years that I've been working on, that people I work with have been doing, that has been used in this big report for the Intergovernmental Panel on Climate Change, to try and understand Antarctica's future. I'm just going to get my water. So just as a reminder, Antarctica is the one at the South Pole, and it's the one with the penguins, not the polar bears. Okay. Hands up if you've heard of Ernest Shackleton. Yeah, great. So lots of you have studied him probably. This was the 1914 expedition, Endurance. He went to Antarctica, didn't end very well. Unfortunately, the ship went down. As you can see here, the Endurance went down. So like I said, a really hostile environment, really difficult to get to go and kind of explore and understand. And one of the things I want to talk to you about is how kind of, in terms of how kind of complex Antarctica is that we often think of ice like ice cubes, like a big kind of block of ice that's just very solid, and maybe if you warm it up, it just melts, melts away. But the really important thing in Antarctica is that ice flows. So you can see really clearly here, this is the dry valleys in Antarctica. And this is a glacier in one of the mountains, just kind of sliding down like icing on a cake. And that glacier flow is important because the more that speeds up, if that ever speeds up, the more of that ice is going to end up in the oceans, and that's going to cause sea level rise. So it's not just about the melting from the warming, it can also be about the glaciers kind of flowing into the ocean more quickly when they reach the sea. Here's a really nice map of Antarctica showing it in a completely different way from usual. So this is showing the speed of the ice everywhere in Antarctica. This is a map from NASA, and it's showing In blue, you can see, it's almost like rivers of ice, like you can see these kind of catchments of ice where it's draining ice from the middle of the ice sheet out towards the ocean. So you can see, for example, have I got a pointer? No. You can see kind of over here on the left, for example, two big glaciers draining into the ocean. I'm going to focus on those a bit more. You can also see the big pink areas. Those are floating ice shelves. That's where the ice has kind of flowed off the ice sheet and off the land and over the ocean. It kind of stretches over in a pancake of floating ice. And those are going the fastest. You can see the pink and red colours. So understanding Antarctica is all about understanding that flow and that change to understand how much it's going to contribute to sea level rise. So it's constantly getting new ice in the middle of Antarctica from snow and losing ice at the edges. It's a kind of constantly moving dynamic place. So it's losing ice, and this graphic shows where the ice has been lost, those two glaciers that I just mentioned before, over at the sort of left-hand side. You can see they're called Pine Island and Thwaites glaciers. You might hear about those in the news sometimes. And this is just showing, like, over and over again, the ice loss, the kind of melting of the red areas where it's got thinner since 1992 up until today. So it's not like it's the whole ice sheet melting, it's the sort of particular bits, and you can see we're focusing on this left-hand side here as well. A little bit over on the right-hand side. There's a few places where it's blue, it's gained a bit of ice from snow, but there's that melting there. So why is that? Well, it's not necessarily melting from the air warming up. It's actually from underneath, because, like I said, lots of that ice is touching the ocean, and so it matters what temperature the ocean is. And this is a picture of the ocean temperatures a little bit below the surface, where it kind of touches the ice. And what it shows is that you can see there's a kind of a ring of blue around Antarctica, which is about -2 degrees. So that's nice and cold. It's not going to melt your ice. But there are parts of Antarctica where the ocean temperatures are much warmer. They're sort of 1 or 2 degrees C, sort of positive, not minus. And so those are in the areas where we're seeing those changes. Now, we don't actually know how much of these changes are down to humans. They might be natural, actually, the fact that warming is there, because the ocean circulation changes all the time and it brings heat to different parts of the world. We're not yet sure if we've caused that. But at the moment, we're getting that kind of warm ocean water sort of tickling under the ice sheet and melting it from beneath. And what we think is that that might be making it unstable. So this area that we're focusing on, that I've ringed in red here, is called West Antarctica. So the other big bit is East Antarctica, and the little spindly bit in the top left is the peninsula. And back in 2014, we had some studies by scientists using measurements from satellites and also using computer models that said, actually, we think these are showing signs of these glaciers look a bit unstable. In other words, they look like they might just keep on losing ice in the future, and it might be quite hard to stop that. So now we try to predict that future with computer models. So now we're looking at a computer model of Antarctica, just a kind of one scenario where there's lots and lots of melting, and you can see over about 500 years, lots of ice is being lost in that West Antarctic part. So I, for example, have PhD students. That's after your undergraduate studies and you go and do a PhD and you become a doctor, who use these models to predict the future of Antarctica. You can actually use that same model that I just showed, that state-of-the-art Antarctic model, in a game. If you go to iceflowsgame.com sometime, and you can use this to control the glacier that you've got here. So you've got a glacier flowing over the ocean, you've got that sort of floating ice shelf, you can see that kind of constant flow, and you've got the penguins there. And what's happening on the right, this is just a demo, is it's changing the ocean temperature to affect how much the ice is melting from underneath. And so the more melting you get, the shorter that ice shelf gets, and the penguin drops off and gets eaten by the seal. You can also build up the glacier with the other slider on the left with snowfall. So that's, remember I said that's the other way that you build up the ice. And so you can maybe save the penguin by making the glacier bigger with the snow. So iceflowsgame.com, it uses exactly the same computer model as I use in my research. We don't have penguins in our model, though. So the other thing that's really key to whether Antarctica is unstable is actually what it sits on. Now, again, we don't really think necessarily that much about what an ice sheet is sitting on. Greenland or Antarctica, they're sitting on rock. But that rock, as I've been sort of saying, some of that is underwater, and that's why it's exposed to the ocean. So this is a little video, and I'm going to show you this is all the sort of rock, the bedrock underneath Antarctica, and the colours show the height. So the red pointy bits are mountains. So you can see here, there's the sort of peninsula bit that I mentioned, the kind of taily bit, and you can see there's kind of mountain ranges underneath Antarctica. And those dark blue bits are where it's deep bedrock that's under the ocean. And what you might notice is that in that West Antarctic bit that we've been talking about, it's really deep blue, it's really deep below the ocean, and that's why it's vulnerable to that ocean warming there and those ocean temperatures. And so one of the things I've done in my research is to try and help scientists to understand how vulnerable Antarctica is. Is it going to be unstable in the future? Would that be the whole ice sheet, or would it just be parts of it? And this is a picture from one of our scientific studies. And what it shows is all the kind of grey and brown bits are the bedrock, which is high up. So it's not below the sea level, so it's not going to be so vulnerable. It's not going to be vulnerable to the oceans. And then the kind of pale blue bits are below the ocean, so they're below sea level, and that's where it's going to be vulnerable. And then the kind of the coloured bits in sort of purple and green and orange, and then sort of yellow, are where we think Antarctica is going to be the most vulnerable, because that bedrock is below sea level, because everything kind of looks the most risky for Antarctica in those places, using those computer models that I just mentioned. So those kind of dark purple bits where we're already losing ice is where we think it's going to lose ice more in the future, and therefore add more to sea level rise. So unfortunately, a few years ago, some scientists thought of another way that Antarctica might be unstable. So instead of thinking about the ocean temperatures from sort of melting the ice from underneath and maybe making those glaciers flow faster, which is sort of adding to sea level rise, there's another idea about maybe the cliffs collapsing at the edge of the ice sheet. And what I mean by the cliff is just something like this, where you've got ice kind of, in a big cliff, sort of abruptly sort of ending like this, like a cliff, because if you think about it, a cliff of ice can't be too high. It would be sort of unstable. Actually, it would start to kind of collapse, because ice has a sort of particular strength, like a mechanical strength, and it would just collapse if it was too high. And the reason we think that that could happen, that we might get one of these high cliffs that would then sort of collapse into the ocean and cause some more sea level rise, is this idea here. So this is a picture from about 2002 of an ice shelf in the peninsula. It's called Larsen B, if you ever want to look it up. And this is one of those floating ice shelves over the ocean. Now, unfortunately, over a period of about 3 weeks, that ice shelf broke up. So you can see there, it's all sort of turned into water and fragments of ice, and there as well. And so the idea is that when these ice shelves break up, the edge, it's not so clear here because you've got mountains, but if you've got sort of one of these big glaciers coming down over the ocean, that would leave behind a big tall cliff. That collapse would leave behind this kind of sheer cliff, and that could actually start to collapse into the ocean. And people have called it all these dramatic things like the Doomsday Glacier. This is the Thwaites Glacier that we just mentioned, that we just saw before. And there were all these kind of worrying predictions that would make Antarctica contribute much more to sea level rise, that it would really speed up sea level rise because that ice was unstable. So we looked at how likely that was. This was, again, some of our research from a couple of years ago. And actually, we sort of thought maybe it's not as likely as we thought. We kind of had a bit of a semi-good news story. It's not sort of as bad as we thought. We thought it was pretty unlikely. But unfortunately, if the greenhouse gas emissions are really high, if we're up at that kind of 4-degree world, we think it still could happen. But we think if we're down at the sort of 1.5, 2 degrees, we think it's not very likely. So kind of partly good news, partly bad news story. So that was our kind of Antarctic diversion. And I think the point about, let's go back. The point about Antarctica is that it's a kind of difficult place to predict. We don't really know if it's going to be unstable. We don't actually know if maybe that snowfall is going to help compensate from sea level rise. So we need more people to kind of go and measure it, to go and explore it, to work on the data, and to use the computer models. And I'll show you how much difference that makes to our future in this picture here. So this is a graph showing from the IPCC report just last month, or 2 months ago. And what it's showing is quite how much difference our choices can make to the long-term future. So we have, on this side here, we have temperatures over 2,000 years looking really stable. So that really kind of stable blue line there. And then I've shown the line of today, so sort of 2021 or so, where we've just had a bit of warming, you can see there. And then the last part of the graph that kind of fans out are different predictions for the next 200 years, 300 years, out to 2300, the year 2300, depending on how many greenhouse gas emissions we put into the atmosphere over those centuries. So we're not just thinking about the next 10 years now, we're thinking about the next 300. And you can see at the bottom end, we've got kind of scenarios of like 1.5 and 2 degrees, the kind of temperatures we've been talking about. But if we just kept on putting in more and more emissions out, we could get to some really huge numbers of 5, 10 degrees or even more. So really temperatures that we haven't seen for maybe tens of millions of years on this planet. And what that does to sea level rise is shown on the right. So if we keep down to sort of 1.5 or 2 degrees, the blue bar is the sea level rise that we would get. And that's kind of 0.5 meter to 3 meters of sea level rise, depending on if we're sort of lucky or unlucky. So that's the kind of uncertainty in the computer models. But if we go for the kind of the red scenarios and we just keep on, and we just ignored all the Paris Agreement, and we ignored all our science, and we ignored all our knowledge about the planet, and we just kept on putting more and more fossil fuel emissions out into the atmosphere for hundreds of years, and we get to those really high temperatures, then we could be going up to 7 meters of sea level rise. Or actually, you might be able to see a little dashed line arrow going up further, and that's if the Antarctic cliffs start to collapse, and it's unstable in that second way. So that shows we've got choices, right? We can keep to the low end or we can keep to the high. But again, it's kind of hard to imagine what a meter of sea level rise does, right? I mean, if we're talking this high, you sort of think, well, is that so bad? Well, a meter of sea level rise makes, like I said, will make coastal flooding more likely. And the kind of scale of a meter is maybe up to 1 in 20 of the world would be at risk of flooding every single year. So they'd have to build sea defences to stop that flooding. This is Mumbai here. But actually some parts of the world would be difficult to protect, even if sometimes people don't have the money to do big sea defences. You know, it's obviously a question of equality as well. But they might not be able to physically do it. So this is Bangladesh. And on the left-hand side, it shows a map of Bangladesh kind of as it is today, and the green areas are where it's very heavily populated. Lots of people living there. But Bangladesh, you might know, is a very low-lying region. It's this kind of delta of various rivers, very close to sea level. Lots of people living all along those coasts, very, very close to sea level, already suffering lots of flooding at the moment. And under a meter of sea level rise, you can see the blue patch at the bottom is the area that would be affected. It would be 15 million people would be vulnerable to coastal flooding, and if we had 1.5 meters of sea level rise, it would be 18 million. So it makes a big difference, especially when you're living, of course, close to sea level. Now, 3 meters, we start to change the coast of the UK. So that was the sort of high end of the lower, the blue bar of sea level rise. And 3 meters is about how much sea level rise is locked up in that West Antarctic ice sheet that I talked about that might be vulnerable to melting, to flowing into the ocean more quickly, might be unstable. So you can see, for example, lots of parts of the coastline. I haven't got a pointer, but you can see sort of over on the east side particularly. Actually, you might not know, but the UK is tipping. Have you heard of this? So this is sea level rise will be worse in the south than in Scotland, because you've got the land rising up in Scotland where we used to have ice in the last ice age that has melted away, but the land is still bouncing up from losing that ice, having all that heavy ice taken away. The sort of Scottish regions and a bit of Northern Ireland is sort of rising up out of the sea, whereas the southern regions are kind of sinking, so sea level rise will be worse in the south. So again, thinking about some of the research that we've done, so we had a study out this year in the summer, which looked at, well, how much can we do to save the glaciers and the ice sheets from melting in the future? We think if we manage to increase all our ambition on limiting greenhouse gas emissions, and we manage to keep down to 1.5 degrees and stick to that Paris Agreement that we all said we'd do, then we could probably really reduce that melting by about half. So we would still see some melting because it's difficult to stop, but we would manage to halve it. So how are we doing so far? And I think this is this is maybe the most important part of the talk, because I think it's easy to get depressed about climate change or think that, nobody's doing anything. But what I'm going to show you is that we are making some progress. We want to make more and more progress in the future right now, but we are making progress. So at the moment we're at so this is obviously a thermometer here, and it's showing different degrees of temperature, where at the moment we're at about 1 degree, just over 1 degree. And remember I said if we double our emissions by the end of the century, we're heading up for more like 4 degrees, maybe even more at the top of the scale. And some of the predictions you hear in the news are often for that very, very warm world, that kind of, that scenario of if we just had business as usual and we just kept on increasing all our coal burning and our fossil fuels and we didn't stop, or we didn't reduce it. Okay, so at the moment, we're predicting for the end of the century, sorry, this is our aim, that's the Paris Agreement, 1.5 and 2 degrees. We actually think we're not heading for that world because we've already got laws in place. All the governments of the world have been putting into place policies and laws that would limit the warming to 3 degrees. So we already think we're not heading for that 4-degree world, that kind of worst case scenario. We already think things are better than we originally thought, and we're down at 3 degrees. But then we can think about what we've promised to do. So the Paris Agreement has lots of promises and pledges of what each country is going to do for its emissions. So like cut by, say, 70% in 10 years, this kind of thing. And so if they manage to put those promises into practice, if they make those promises law, and if they manage to increase make the technologies better and reduce our emissions and go to renewables and all those different things that we know about and we're going to talk about today, then the predictions go down to 2.5 degrees. So we're not quite yet down to our target of less than 2 degrees, but there's some uncertainty around these numbers, and even the lower end of the predictions for the promises is actually just touching on 2 degrees. And the thing is, over the last few years, these numbers have been coming down and down. So when I started looking at this website, climateactiontracker.org, which updates every few months or even more frequently than that, the numbers were all much higher, but every few months they come down because all of our policies get better, all our laws get better, we're making progress in our technologies, and all our promises get better. We get more ambitious and we say we're going to cut more emissions. So people are doing something, we are making progress. We're not doing it fast enough yet, but we're getting there. We are slowly coming down the scale, and every little bit of CO2 that we avoid emitting will help bring us down that scale. So you might think, well, what happened with COVID to our emissions? Big question I get asked a lot. This is showing our CO2 emissions from about the year 2000, going up through the years to 2020, where we saw a decrease. So you can see originally it was kind of increasing about 3% each year, then it slowed down to a bit less than 1% each year, and then in 2020 the emissions dropped by 7%. So it shows that our actions can have a huge impact on our emissions. We have to keep that line going down if we want to meet these targets of the Paris Agreement. We have to keep on decreasing our emissions every year. So that's really difficult, right? We don't want to do it the way we've done it with COVID, because that's been really difficult for people. We have to think of different ways to get that same result every year of decreasing and decreasing. And so the most important thing at the moment that you'll hear in the news is this thing called COP26. Now, who's heard of COP26? Yeah, so you might hear more about it today. So that thing, that Paris Agreement, that big global decision that we made back in 2015, that was called a COP. It stands for Conference of the Parties. It's kind of, global kind of like getting together of all the countries. And this one next month is happening in Glasgow. It's happening here in the UK. It's really important. We are leading this big decision of all the countries of the world to get together and make new promises that are more ambitious to bring those lines down, to bring those temperature predictions down. Okay, so we need it to be really, really ambitious, and people are all the eyes of the world are on us or on Glasgow to make that happen. So in case this is making you think, oh, right, what can we do? What's happening? Well, I just want to sort of do a little promotion. We have a Radio 4 series all about people who are going out there and making a difference, who are changing the world, who are working out how to reduce our emissions, to preserve nature, like our trees and our peatlands and our ocean life, particularly to decrease those emissions, to make that happen, to make those policies and pledges and promises happen. So if you ever have Radio 4 in the background, you might hear me pop up talking about one of these different ideas. Our new series is on next week, actually. And so just finally, if you want to do something on climate change, so first of all, I can talk about how to become a climate scientist like I am, and study, make these predictions for the future, and try and understand the science of places like Antarctica or the different parts of the world, whether it's the oceans or wildlife. And of course, science, physics, chemistry, biology, science is going to help, maths is going to help, computing if you're interested, design and technology, people go into engineering, of course, and geography is really, really important. Geography covers the whole planet and all the people on it. It's about how to put everything together into one big picture. But even if none of those subjects are for you, we still need you, because climate change affects every single thing on this planet and every single human. And so we need things like art and music to help people understand and think about the future and why climate change is important. I work with artists on that. We need historians to understand how we've acted in the past and how quick we have been to make big changes like the Industrial Revolution, because we need a new revolution now. And psychology, we need to understand how people think and work so that we can change our behaviour and help to motivate people to take action and keep feeling optimistic and inspired. So if you want to help on climate change, anything that you do, anything that you're interested in, you can apply to climate change, because it touches everything in our world. And I'll just leave it there and take some questions, I think. Thank you.
A couple of minutes.
Yeah.
Right, guys, does anyone have a question for Dr. Edwards out there? One there. You have to speak loudly.
Yeah. Isn't it true that over 80% of global greenhouse emissions are being produced by just 100 companies in the world?
Yeah, I think that's right. Yeah, so there's lots and lots of discussion about the fairness of emissions. That's a good question. So, for example, it's only a small percentage of the world's population that do the most flying, and it's a small number of companies that produce emissions. Obviously, the oil and gas companies are producing emissions. But really, we have to sort of also not think too much about the blame game. I mean, people will sort of blame different countries or different technologies or different people, because really we need to think about how we all get together, all companies, all people, all countries. It's not about just picking on a couple of different businesses or a couple of different companies. We've got to all figure out how to get down to basically zero emissions to stop more warming happening. Yeah.
Any other questions out there for now?
This one here, I think, on the front.
If we worked by solar, how much would that increase the emissions?
Yeah, and solar power is really amazing. Like all the predictions for solar power were that it would sort of grow slowly, like how efficient the panels are and stuff. And it's exceeded all expectations. It's got incredibly successful over the last 10 years or so. So definitely solar power is really important. You can have solar panels to make electricity, and you can also have solar panels on your roof that just have hot water, have the water going through the panels, and it directly heats your water on the roof. So you make all your water for your central heating go onto the roof. So solar is really important. But it's a kind of about thinking about every single possible idea we can get. It's not about relying on one thing. We've got to have the solar, we've got to have the wind, we've got to have lots of different ideas all put together and sort of throw everything we can at the problem. Yeah.
Probably got time for one more. I see a hand in the back there.
What do you think all these solar panels and batteries for electric cars to recycle? And it's really hard to recycle them. So they will cause even more problems in the future. So it's just maybe one-time solution for the problem.
Yeah, it's a great question. So there's been, if people didn't hear that or if they don't know, there's been concern about the batteries for electric cars, and there's other things you can use them for as well, but electric cars, because the materials you use, it can be damaging to mine them from the environment and it can be difficult to recycle them. So it's a great question. People are obviously aware of the problem and figuring out better ways to do it. But also, there's a whole brand new kind of set of batteries that use different materials that are much more environmentally friendly. So they're all being invented now so that they can come out in the next few years. And one of our radio programs that I just mentioned, 39 Ways to Save the Planet, in the next 2 weeks is about exactly that. It's called Better Batteries. It's about exactly all the scientists and engineers that are working on that problem so that we can have electric cars without worrying about environmental pollution of the materials and recycling, that we make that easier. Yeah, good question.
Okay, I think we'll have to leave it there, so thank you very much.
Thank you.